Okay, so this was the example we were looking at. So again, remember this is scores on a national achievement test for a group of 10th grade students. And this is where I guess we were last time. So you guys should still have your percentile graph, yeah? Okay, so we had just started answering those questions. So this is that first part, which is asking us to find the approximate percentile ranks based on these scores. So we've got 220, our next score is 245, 276, 280, and 300. And I think you guys had written those numbers down last time. So go ahead, just like we did last time, try and get those answers, and then let's compare our answers for these remaining four scores. We had already done 220. So for 245 as your score, what would be that percentile rank? So again, just to show you how we would go about doing this, again, you kind of have to find out approximately where 245 would be. So again, remember the difference between each of these scores is 21 points, basically. So 245 would have to be where? If you had to approximate a position for 245, where would you put it? Halfway? Less than halfway? Yeah? A little less than halfway? Because halfway would be, if 21 is the difference between our two markers, then halfway would be about 10.5, right? So I would say look at the difference between 238.5 and 245 and then kind of decide. So I would probably put it about a quarter of the way from 238. Oh, maybe right there. And again, the idea is keep going straight till you get to that curve of your percentile graph. And remember, again, this was basically an ogive graph that we did. And then you have to figure out what that horizontal percentile rank would be. So again, using a straight edge would be helpful. I don't know. What would that percentile rank be? So it looks like about a quarter of the way. So yeah, maybe 23. So remember again, these are not percents, they are percentiles. So this will be the 23rd percentile. And the textbook is giving you the answer of 24. So again, I'm not sure how the textbook is coming up with that, other than they're using a computer program to come up with that and probably get an accurate answer. But based on the graph, again, you're gonna have to make your best guess, right? All right, so same process for the other three scores, 276, 280, and 300. 3 today, so let's go through this and see what kind of answers we come up with. So for 276, what did we have? Say that one more time. Okay, so 276 would be really close to that 280.5. So again, if we try to do this on our graph, pretty close to that 70 mark is what it looks like. Oh, come on. Okay. So where approximately would that be? Yeah, your textbook is saying about 68, 69. And again, that's 68th percentile. For 280, which is literally going to be like a hair before that 280.5. So these two should be pretty close to each other. And what does this guy come out to be? And you know, my lines are not straight because I'm using a paper instead of a ruler. So I will be slightly off. You guys may be a little bit lower than that. But again, what kind of number does that look like? 79, 78? Yeah. The official answer is 76. As long as you're in that neighborhood of a couple points off, we're going to be okay. As I was talking to Michael, we can't really hope for accuracy because everything is so, well, we're guessing our positions at this point, right? Okay, for 300, what did we get? And this marker here is 301.5. So 300 obviously would be just slightly off from there. So 300. And where does that put us? Oh, come on. Nope. It's slightly above 90. So what would we say that number is? Yeah, I'm thinking more like 92. But again, officially, 94th. Yep. I am very, very suspicious that they have not used a graph, but have actually done the calculation to come up with these numbers, or used a computer program to do their graphing. Okay, so this was looking at the scores coming up with your percentile rank. Now, if you're given the percentile rank, they want to know what corresponding score that would have. So that would be 15th percentile. So 15, of course, would be halfway between 10 and 20. So hopefully that guy will work out a little bit better. So this is, of course, same process. Go on till you hit the curve and then draw your horizontal line. From there, nope. something like that. So what would we estimate for 15th percentile? What number would this guy be here? Between 217.5 and 238.5, but more than halfway towards 238.5. So halfway between that would be 228. So between 228 and 238, what would you assume that value to be? 230-ish? Okay. So your textbook says that should be 234. Okay. All right, guys. I really want to move forward. So I'm going to tell you what your textbook is telling us for the others. For the 29th percentile, you should be approximately at a score of 251. For 43rd percentile, you should be at 263. For 65th percentile at 274. And the last one is 80th percentile at a score of 284. Okay. Because as you can see, this is a pretty slow process since we have to draw each of those individual lines. If you see something like this on your exam, we're of course not going to give you like 10 parts to the question, right? We're not going to have you find scores and percentiles. So maybe we'll give you one percentile and find the corresponding score, maybe give you one score and find the corresponding percentile. But now obviously this is a good practice. You should see something similar in your homework with this percentile graph. So just kind of, practice with that and let me know if you have any questions. Any questions at this point? Okay. All right, if we go back to our handout, this is kind of where we had stopped right after we saw this example. So we're actually picking up with this last paragraph here. So this is kind of what we saw as tediously as that example went. You only get approximate values when you are using the percentile graph. So of course we want to try and use something more concrete, and that's where we get these mathematical methods they're talking about. They can be used to find the approximate percentile rank of a data value, or to find a data value that would be corresponding to the percentile. But obviously you're going to have a little bit better approximation when you're using a method as opposed to just looking at the graph to come up with that. So as you can see, your percentile formula here. So we're saying the percentile corresponding to a given value of X is computed using this formula here. So they're looking at whatever is that data value X for which we're trying to find our percentile rank. You actually start by looking at how many values you have below that X value. You're adding half to that. So that's your standard. You're going to add half total number of values. And then of course you're multiplying by N. And as you can see with this little statement here, they're saying when your data set is really large, which means you have more than 100 or more than 100 data values in there, you're actually going to get more accurate or at least better approximations on your results than you would with smaller data sets. So just as an example of how we would calculate these percentile ranks, using the formula, you were looking at the number of traffic violations here recorded by the police department over a 10-day period. So you can see what those numbers are. They're asking us to find the percentile rank of 16. So the first thing you're actually going to have to do is put your data set in order, okay? Because remember, we need to count how many data values are below that given X value. So start by putting it in order. They're talking about finding the percentile rank of 16. So that's 3 data values below 16, you will again notice we did not count 16 in that total. It's how many are below, right? So that's 1, 2, and 3. So that's 3 plus 0.5. That's a total of 10-day period. So we have a total of 10 values multiplied by 100, and you get your percentile rank, okay? So we are basically saying that the value of 16 has a 35th percentile rank. So remember that only 35% of the values fall below, right? The remaining values will fall above, which will be again what? If 35% falls below, how much is above the value of 16? 65, yeah, again 100 minus 35. Alrighty. Just a note here, we're saying that one assumes a value of 16, means theoretically any value between 15.5 and 16.5. So we're talking about a range of values here. Just the same example of traffic violations. They want to know what is the percentile rank of 24. So if you look at that list that we had in order, 24 is now the second largest value, right? Which means we are going to have 8 values below 24. So that's your 8 plus 0.5 divided by 10. And again, multiply by 100 to get your 85th percentile. So again, that's what we would say, that 85% of the data values would fall below 24, or 24 is higher than 85% of the values. Okay, so this other part is actually talking about finding the data value when you're given a percentile. We'll come back to that. Let's at least look at an example where we're finding the percentile rank. Okay, how about example number 23? Okay, so number 23 here. They're asking us to find the percentile rank for each value in the data set. They're saying the data represents the values in billions of dollars of the damage from 10 hurricanes, right? Do we need to arrange the data set in order? It already is. Okay, so they've done one little thing for us. Okay, so now we're trying to find the percentile rank, right? So how about we start with, and we're not going to do all of them, but let's look at number 2.5. So let's find a percentile rank for the data value of 2.5. So go ahead, write down all that information. Remember, you're using the percentile formula. So how many data values are below 2.5? Add a half to that, divide by the total number of values you have, and then multiply by 100 to get your percentile rank. So how many data values are below 2.5? Six? Below. 5. You do not count the number itself, right? Just the numbers below. So that's going to be the 5 values below 2.5. So that's going to be 1 second. So percentile rank for data value of 2.5. $55 sounds better. So that's 5 data values below 2.5. You are adding 0.5 to that. The half? Yeah, I gotta be careful. Your total data values are 10, right? Because they are telling us the damage from 10 hurricanes. You can obviously add those numbers up. So that's 10 multiply by 100, and then of course that came out to be. And remember, this is percentile, it's not percentage. You will lose points for that, because we have to understand the difference between a percentile and a percentage. Okay, what do you think we would get if we tried to do the percentile rank for, let's do 6.2. So let's go back to the example so you can take a look at it for 6.2. You have an answer? What you got? Yeah, because there's 7 values below 6.2. You're adding the 0.5. Divide by 10, multiply by 100. And again, that's 75th percentile. Questions on that? So just the main thing I would say is make sure you're not counting the number itself, but just what's below it, and you should be fine. And like Valerie mentioned, don't forget that 0.5, right? Because it'll change your answer. Okay, so now calculating the data value based on the percentile rank, which is what that next set of formulas is about. So this one here, again, obviously arrange your data in order from the lowest to the highest value. Now here, another formula, C equals N times P over 100. So N again would be the total number of values. So if you just look at the hurricane example, that's 10 total values. P is going to represent the percentile. So if they say find the, I don't know, 80th percentile, that's what you would put in there. And then of course we're dividing by 100. Now here's the part that we got to be careful about, how to evaluate this data value. So the answer you come up from this little calculation, N times P divided by 100, if that number comes out to be not a whole number, then they're saying round that number up to the next whole number, right? So if it came out to be, I don't know, 6.7, round it up, make it a whole number 7. So they're saying starting at the lowest value that is in your data, count till you end up at that number, right? So count over to the number that corresponds to your rounded up value, and that's what we would say is our data value. Now, if this calculation for C comes out to be a whole number, then they are saying use the value halfway between the C and the C plus 1 position when you are counting from your lowest data value. So it's really interesting on how they want us to find the position where that percentile data value will be. If you did not get a whole number in your calculation, round that up to the whole number, and then counting down in your data value set, you can come up with that. If you get a whole number, you're actually using the halfway value. So if you got 6 here, you're actually looking at 6.5, right? That would be halfway between 6 and 7. And that is where you would count from your lowest data value. So again, using our traffic violations example here, they are asking us to find what value would correspond to the 65th percentile. So you've got total number of data values, which is 10. Our percentile is 65, divide by 100. Now, what's the one thing you are noticing about 65 here? Not a decimal, right? When we're working with percents, we always convert them to decimals. But again, this is a percentile, so it does not get converted to a decimal. So just again, that difference between, is it a percentage value or a percentile? So again, be careful. So again, 10 times 65 divided by 100 gives you 6.5. So 6.5, not a whole number, which means we round it up to a whole number, and we're saying C becomes 7. So then you start counting, and number 20 is going to be the data value that corresponds to the 65th percentile. So that's kind of how these calculations work. So they're telling you the value of 20 corresponds to the 65th percentile. The C is not giving you what the data value is, right? The C is the position of where you will find your data value. So that was if you did not get a whole number, round it up, and then count the position. Now, going back to that example, for traffic violations, they're asking us to now find the data value for the 30th percentile. So same thing, 10 times 30 divided by 100, which gives you a position of 3. So a whole number means you go halfway between that number and the one next to it. So you would be going halfway between the 3rd and the 4th values. So in your list, halfway between the 3rd and the 4th values, 3rd value is 15, 4th value is 16, halfway between that is 15.5, right? So 15.5 would correspond to the 30th percentile. So they're asking you the same question in number 23. They're asking you to find what value would correspond to the 40th percentile. So for the 40th percentile, so for 40th percentile, you've again got 10 total hurricanes, right? This is the 40th percentile, and divide that by 100, what do you end up getting? 4. So since this is a whole number, we need to look halfway between, hold on. The 4th and the 5th position. Do I want to say position? Sure, why not? So halfway between the 4th and the 5th position, where would that put us at? Very good, halfway between 2.1 and 2.2. 2.15, yeah, very good. So you don't need to find that average, right? Just add the two numbers, divide by 2. So that would be 2.1 and 2.2. So the data value 2.15. Again, basically, like I said, let's do that in red. Add the 2, divide by 2 to find your data value. So 2.15 would correspond to the 40th percentile. If this number C had come out to be a decimal, you would have just rounded it up to one decimal place and then counted that position. So 2 distinct calculations depending on what your C value comes out to be. Okay. Are we comfortable in finding the percentile when the data value is given to you, which was those first 2 examples? Any questions on that part? Okay. How about when the percentile is given to you and they're asking you to find the data value? Okay. Alrighty. How about okay. Just the 40th percentile part, you don't have to find the percentile range. But let's do one more example where they're asking you in number 21 to find what value corresponds to the 40th percentile again for this guy. So what's the first thing we need to do here? Put numbers in order, very good. So which would be our smallest value here? Okay. 228. What would be next in line? 489. Okay. 524. 597. 623. 659. 736. 777. That would mean he's the last one. So this one, of course, is talking about the average weekly earnings in dollars for different types of industries. So now we're calculating the 40th percentile. So how many total data values do we have? 9, right? Okay, so this guy is number 21. Okay, let's save that, close that. So the first thing you are going to do is find your C value. That's 9 total data values. This was again the 40th percentile. Divide that by 100, right? 3.6. Very nice. So when it's a non-whole number, you do round it up to a whole number. So this one, you don't have to go halfway, right? You just go to the position itself. So that's the 4th position, which is going to be 597. Questions on that? Okay. All right, so that was example number 21. Let me see if I can clear this out. There we go. Yes.
This only works, this doesn't work with data sets.
This does not work for what?
Group data sets.
Group data sets. Percentile rank. Trying to think. I think you would be able to get the grouping, but maybe not the exact data value.
Because it's already arranged.
Because it's yeah, exactly. So you may be able to say, okay, it's going to fall in this one, but then we may not be able to get the exact answer. That's an interesting question. I've actually never seen them done a calculation of percentiles for group data. So I wonder if that's the reason why they just never bothered. But you know, I mean, I don't know, mathematicians and statisticians, they love challenges. I'm surprised they haven't done that. I will look it up. I will see if I can find any information on that. Awesome, very good, yeah. Did anybody else have a question? So you've seen the 2 calculations for the percentile rank. One, when you get a whole number, you're supposed to go halfway between that position and the next one. When you get a decimal answer for C, you round up to the whole number and then use that as your data value. So yeah, it's a pretty interesting calculation here. All right, so percentiles can be broken down actually into quartiles and deciles. So quartiles, of course, means you're looking at the 25th, the 50th, the 75th percentile, right? Because you're breaking that up into, I guess, quarters in a way. So that would be quartile 1 at 25th percentile, quartile 2 at 50th percentile, and of course, quartile 3 at 75th percentile. Your quartile 2 also happens to be the midpoint for your data values. So you can kind of see that little explanation here. You've got that little timeline to kind of help you out. So they're saying that you can calculate your quartiles by basically using that same percentile formula where we had the number of data values below x plus 0.5 over n multiplied by 100. You can actually use that if you're trying to find the data value that would correspond to the percentile. You can still use the C equals n times p over 100. And in that case, they are saying for quartile 1, you would use 25 for the value of p. Same thing, quartile 2, 50. Quartile 3 would be 75. But then they actually have this other method also to help us out. So same thing, start by arranging your data values in order from smallest to the largest value. Find the median, which would be your quartile 2, right? The halfway point, 50th percentile. And then you're actually, after you find that midway, halfway point, then you're going to find the halfway for the first half and the halfway point for the second half, which would be your 25th percentile and 75th percentile, which would be your quartile 1 and quartile 3. So they're actually going with that idea of median. So set your data set from smallest to largest, find the halfway point, which would be your median or quartile 2. Now we've broken up our data set into two parts. So between the smallest value and the median, find your median again, which would make it quartile 1. Between your median or quartile 2 and your highest data value, find the median again, which would be your quartile 3. So let's take a look at our traffic violations example here again. So we've arranged it in order. Now these were 10 data values. That means your median is going to be between the two centermost values, which is halfway between 18 and 19. That comes out to be 18.5. This is my median or quartile 2, 18.5. Now, 18.5, of course, is halfway, which means the first 5 numbers can now be used to find quartile 1, which is going to be the centermost point, which comes out to be the number 15, quartile 1. The last 5 values, again, find the median, which will come out to be the value of 22, right? So you kind of have to see, do I want to use the formula or do I just want to find those 3 different medians of my set to come up with my quartile 1, quartile 2, quartile 3. You will need these calculations when you talk about graphing a box plot, which is what we're going to be doing with 3.4. So we will ask you to find the lowest value of your data set, the highest value of your data set, quartile 1, quartile 2, quartile 3. Taking the difference between quartile 3 and quartile 1 gives you what we call the interquartile range. Right? Think range because range is usually between the highest and the lowest values, right? The difference between those numbers. But this is interquartile, which means we just want to know how far is your quartile 1 and quartile 3 data values. So that's your interquartile range, which is Q3 minus Q1. So if you were finding the interquartile range for this example, you would be taking the difference between 22 and 15, which would come out to be 7, and you should be able to see that on top of this page right here. So it's really just one calculation which is coming up with all of these other ones. So find your quartiles, and then once you have those, take the difference between quartile 1, quartile 3, you've got your interquartile range. In that same sense, how we had talked about standard deviation, the more variable your data set is, of course, the difference between your quartile values is going to be larger, right? So the smaller the interquartile range, the more concise, less dispersed your data is, the larger that interquartile range value is going to be, the more dispersed, the more spread out your data is. Deciles, same exact thing, but now deciles are looking at every 10th percentile. So of course that would be the first decile would be the 10th percentile, decile 2 would be the 20th percentile, decile 3 would be the 30th percentile. So as long as you're comfortable with percentiles, you should be able to come up with your quartiles and deciles because they've just taken it down and broken it up into different denominations is basically what they've done. So you can kind of see that summary for percentiles, deciles, and quartiles. The standard score or z-score was the first thing that we had talked about, which was just finding out how far away from the mean you are. If it's a positive number, your z-score comes out to be, if it's a positive z-score, that means you're above the mean. If it's a negative z-score, you're below the mean, right? So that gives you the position with respect to the mean. So before we get into outliers, I would like to do a quick calculation. Yeah, let's look at 25 here. So this is for a recent year that shows the taxes in millions of dollars received from a random sample of 10 states. So they're asking us to find the first and third quartiles and also the interquartile range. But you know what? I would also like you to find quartile 2. So find all 3 of the quartiles and the interquartile range. So first and third. And the second quartile also. So then what's the first thing we do? Put them in order. Very good. So where do we start? 6. 11. 11 again. 13. 24. 25. 32. 'Okay, so that should be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So finding quartile 1, quartile 2, quartile 3, and the interquartile range. And we use the abbreviation IQR for the interquartile range. So I would probably start with quartile 2, right? Find the midpoint first. And then you would have to do quartile 1 and quartile 3. So anybody have the value for quartile 2? 24. 19.5. You said 24? Okay, so why did you get 24? Because you've got a total of how many data values? No, I cannot do that. So you've got 10 data values, right? Which means your midpoint, again, remember we have a position formula for the midpoint, which was n plus 1 divided by 2. You've got a total of 10 data values, which means you're looking at a position of 5.5, right? So that would be the 5th and the 6th position. 5th and the 6th position would be 15 and 24. So you would add those two numbers and then divide by 2, which would give you your midpoint, quartile 2, and that's 19.5, yes? Okay, now for quartile 1, what do we do?
Oh.
Yeah, go ahead. The first half, very good. Very good. So now, because we know between 15 and 24 is midpoint, the midpoint, So now you just take that first 5 values going from 6 to 15, and the centermost is going to be 11. So this guy is quartile 1, right? The last 5 values is going from 24 to 71, and again, the centermost value in that is 32, which is going to be quartile 3. So that's 11 and 32. So what's our interquartile range? 21. So it's really straightforward calculations, but you just have to be careful about that positioning. If you're 1 off, your numbers are going to be off, right? Did anybody have questions on that guy? Yeah? Are we okay? Alrighty, let me get rid of that. Nope. Okay. So we had talked about outliers before. What do we understand by outliers again? Exactly. So it's going to be something that's going to stand out from the rest of your data value. And of course, you can see that little definition here. They're talking about, of course, the outlier can affect your mean and standard deviation. And again, if you guys remember, we had talked about that example where you had the technicians, the manager, one other person, and the owner. They were all making like 18 to 24,000, but the owner was making 100,000. It may be, I'm not sure which handout that was in. So that owner's salary of being a 6-figure salary compared to the others was pulling that mean to a higher value, I think like 40,000 or something. So we know an outlier can really affect our mean and standard deviation. So they're saying since these measures are affected by the outliers, they are called non-resistant statistics. They're not resistant, right? They're making that change based on that calculation. But if you use a median and an interquartile range, they are not affected by the outliers, right? Because the median goes for the centermost position, so it's really not worried about the highest or the lowest value affecting it. Interquartile range is going from quartile 1 to quartile 3, which are again median calculations for those parts of your data set. So again, since it's not taking into consideration the lowest or the highest values, you're not going to see that outlier making a big change on your measure of central tendency and your measure of dispersion. So that's why those are called resistant, because they resist those outliers. So they're called resistant statistics, your mean and standard deviation, non-resistant. So they're talking about how you can actually identify if your data set has an outlier. Because you know, a lot of times your outliers don't necessarily have to be so out of bounds that it's obvious to us that we have an outlier. So they're talking about, again, start by arranging your data in order, find your quartile 1, quartile 3, which means you can also find your interquartile range. Then once you have your interquartile range, multiply it by 1.5. Whatever answer you get from here, subtract that from quartile 1, add that to quartile 3, right? So whatever answer you're getting from step 3, subtract from quartile 1, add to quartile 3, and then basically you should be able to see if any of these values, if your data set would have a value that falls below or above those calculations. So looking at this set here, we're going from 5 all the way to 50, and you can see that breakdown. So finding quartile 1, quartile 3 is 9 and 20 respectively. Your interquartile range, of course, comes out to be 11. Multiply that 11 with 1.5, you're getting 16.5. Now the idea is subtract the 16.5 from quartile 1, add the 16.5 to quartile 2. So when I subtract, I am getting negative 7.5, and of course there's no number smaller than negative 7.5, right? So we definitely don't have an outlier on the smaller side. But when I add 20 with 16.5, that's giving me 36.5. So 36.5 would be somewhere in here, which actually means 50 is a number larger than 36.5. 50 is the outlier. And that's kind of what I'm talking about. Sometimes it may not just jump out and say I'm an outlier, which you can kind of see. We stayed between 5 and 22 for the most part. That 50 is definitely a little bit higher than the rest of our numbers, but this gives you a good way to know, oh yeah, I definitely have an outlier. So it's basically the idea that you are taking your interquartile range, taking a 1.5 of that value, so that's your 16.5, subtract from quartile 1, add to quartile 3, and anything that falls outside of those values are considered outliers, okay? So if we had to do a similar calculation, and you know what, let's use this example right here that we did, because we've done all those calculations, so we don't have to start over. So take your interquartile value, and here we are checking for outliers. So interquartile range, multiply by 1.5, what will you get? 31.5? Okay. We're going to take 31.5 and we're going to subtract it from quartile 1 and add it to quartile 3. So what was our quartile 1 here? Oh, sorry. Not. Yes, 11. You're adding and subtracting 31.5. So 11 minus 31.5, what do we get? Negative 20.5. And quartile 3 was 32. So 32 plus 31.5. So this is negative 20.5 to 63.5. Negative 20.5 to positive 63.5. Do we have an outlier? Yeah, so in this case, 71 is an outlier. Okay, there we go. They're just talking about why you can have outliers showing up. Of course, you know, there can always be a chance of human error. So was there a measurement error or an observation error? Did you know, a variable get measured incorrectly, which would again kind of come down to the researcher? Was it just a recording error? Did we just, you know, write the number incorrectly? They are talking about it could have been typed incorrectly or maybe just written down incorrectly. Could have been obtained from a subject that was not defined in our population, and maybe as a researcher, again, we did not catch that. So let's say they're saying, suppose test scores were obtained from a 7th grade class, but you actually happen to have a student who's technically in 6th grade taking a 7th grade course, then technically that student's data should not have been counted, right? So maybe that's why an outlier is coming in there, because maybe that student is taking a 7th grade class, but they're not quite at par with their classmates in that class, right? So maybe their scores maybe on the lower side or something. And then the last one, they are saying it could just be there's no error, no recording error, typing error, none of that. And it actually is a legitimate value that happens to be there. And in that case, you as a researcher have to make the decision, do I want to keep that data value or do I want to leave it out? So again, that's going to be something you will have to see what happens when I take that outlier in my calculations. What kind of result do I get if I leave it out? What kind of result do I get? Am I getting a better representation by leaving it out or a better one by keeping it in? You know, a lot of times it's not going to be just a black and white scenario. A lot of times you're going to have to make that decision as a researcher. And I think that's kind of what they're talking about here. And then, of course, in chapter 4, which is our next chapter, we should be getting into normal or bell-shaped distributions. So they're talking about how you could have outliers when you're looking at standard deviation values outside of 3 standard deviations. All right, guys, so that is your 3.3. Section 3.4, like I said, is really getting into Boxplots, which uses the 5-number summary, which is mainly what we did in this last part of section 3.3. Okay, so they're just kind of talking about what the traditional statistics does. So everything we've done so far has been part of that traditional statistics, looking at our histograms, frequency polygons, ogives, frequency distributions, using our mean and standard deviations to help us summarize the data. But then you can also have exploratory data analysis, like they're talking about here, using the stem and leaf plot. We had done that in our previous section. So when you're talking about EDA, the exploratory data analysis, we actually use median as our calculation for central tendency. You're using interquartile range that we just talked about. Remember how we said the outliers do not affect these calculations. They are your resistant statistics. So those are the values we're using in EDA. And for a graph, we actually use what we call as a box plot. Some textbooks like to call it the box and whisker plot, and I guess you'll see why it's called the box and whisker plot. It's kind of funny that they have that name for it. And then they're just getting a little bit into about who came up with this, John Tukey, who really came up with this idea. So your 5-number summary is exactly what we talked about. The lowest data value from your set, the highest data value, quartile 1, quartile 2, quartile 3. And those are the exact 5 values we used when we are graphing a box plot. So for your box plot, you can see the definition right here, but start by finding that 5-number summary. And then basically all you are doing is you are drawing a horizontal axis, place your scale on it. So depending on what your lowest data value to what your highest data value, we're gonna have to spread it out evenly. They're saying the scale should start on or below the minimum value, and it should end at the highest or maybe a little bit higher than the maximum data value. So again, you don't have to start at 0 like we normally do for our x-axis, right? And then basically you're going to find your lowest data value, the Q1, Q2, Q3, and the highest data value. And the graphing of this is basically from quartile 1 to quartile 3 is where we do the actual drawing of the box. From the minimum value to quartile 1 is where you draw just a horizontal line. From quartile 3 to the highest data value, you again draw your horizontal line, which is your whiskers. Okay, so the box, and then just horizontal lines outside of it, which gives you your data. So looking at, your whiskers for the data. A number of meteorites found in 10 states. For the US, again, arrange your data values from smallest to largest. We find our median, our quartile 1, our quartile 3. Of course, we know the highest and smallest and largest data values, which will be 30 and 296. So this is where we are drawing our horizontal scale. And then you mark your lowest data value, quartile 1, quartile 2, quartile 3, highest. data value, okay? Now, even though I told you don't have to start at 0, because these data values were going from 30 to 290, that's why they started at 0. So again, that can be a decision you can make. I personally don't like this scale, because this is kind of like that percentile graph, right? Because now you're again guessing where you need to make this marker. So I would have probably put more markers in there to help us out, but you still get a general idea here. So this is what I was saying. These are your whiskers at the end, and then your box in the center. So from quartile 1 to quartile 3 is the box, and then the outer numbers will be just these horizontal lines. Now you can still talk about what kind of distribution your data value has, because if these lines are relatively the same length and the quartile 2 kind of falls in the middle of your box, you can say you kind of have that symmetry, right? But here you can see my median is kind of more towards the left-hand side. This length is smaller than this length here. So basically they're saying if the median falls to the left, then you're looking at a positively skewed data. If your median falls to the right of the center, you're looking at your negatively skewed data. And then same thing with the length of those horizontal lines. If they're about the same length on both sides, we can see our distribution is approximately symmetric. If the line to the right is larger than the line to the left, again, positively skewed. If the left line is larger than the right one, it's negatively skewed. So you should be looking at those distribution of these data sets also. So just as a quick example, again, here, we're talking about graphing 2 or more data sets on the same horizontal axis. So here we're looking at speeds in miles per hour of a sample of wooden roller coaster and a sample of steel roller coaster. Same thing, find your 5-plot summary, and then 1 horizontal axis, 2 box plots, right? So just be careful about that. You do not repeat that horizontal axis for each, because we're comparing them. So you're basically just doing 1 horizontal axis and then stacking your 2 box plots. So this is our wooden coasters. This is our steel coasters. And you will notice in all of these examples, we actually write down the actual values for our 5-plot summary. Because again, just looking at the scale, you're guessing what those values are. But if you actually put those numbers in, then as a viewer, it makes it easier for them to see what exact numbers you were looking at. So in terms of skewness, what would we talk about these 2 box plots here?
The wooden one, since the left line is larger than the right line, would be negatively skewed.
Negatively skewed, but then looking at the box itself, what would you say? Pretty symmetrical, yeah. So it's somewhere between being left skewed to being symmetrical, right? But what about the steel roller coasters?
The opposite. The box is fairly symmetric between the highest and lowest values, and then the values within are negatively skewed.
For the larger and the smaller data value? Is that what you're talking about? Yeah, this one I would actually say is more positive or negative? Negative, right? Just for the reason that this line is significantly longer than this one, and then your median is not towards the center, right? It's actually more towards the right-hand side. So both line and the box are actually leaning towards it being negatively skewed, sorry. Okay, so I actually would like to look at an example for this. And you know what, to save time, how about we fall back to example 25. Since again, we have our interquartile range, we have our Q1, Q2, Q3 values, and let me put that example up. So smallest data value, largest data value. Mm-hmm. And the largest? 71. 71, very good. Alrighty, so now let's talk about a box plot, our 5-number summary. So lowest data value was 6, quartile 1 was 11, quartile 2, 19.5, quartile 3, 32, highest data value 71, and then we also want our interquartile range, which was 21. Okay, so to try and put this on a horizontal axis, how would you scale if we are going from 6 to 71? 0 to 80, and in increments of 5s. Okay, so they're saying 10. So go with whichever one you are more comfortable with. So if you're starting at 0, can I get 5s in here? I'm gonna try. 5, 10, 15, 20, 25, 30. Again, guys, remember these have to be equally spaced. Not bad. Okay, so you are starting at 6, 11, 19.5, 32, 71. Okay, quartile 1 to quartile 3 is the box. So that's 6, 11, 19.5, 32, 71. Going from the lowest value to quartile 1 is a horizontal line. Going from quartile 3 to the highest value is also a horizontal line. I am doing it freehand. You're not allowed to do it freehand, so please be careful about that. For the exam especially, have evenly spaced out scale on your horizontal axis, and then of course have a ruler to help you draw the box and those horizontal lines. And this guy was for taxes from 10 states. So give your Boxplot a title. Yes.
So wasn't the values in billions? Do we have to mention that on the graph in some way?
That may actually not be a bad idea because this is in millions of dollars. Yeah. I don't know, maybe somewhere along your horizontal axis. Thank you. So honestly, the only thing they are really doing in this section is talking about the box plot. They could have pretty much combined 3.3 and 3.4 together, but I think they just wanted to emphasize that these calculations are a little bit different than your mean and standard deviation, where outliers have an effect, but with the exploratory data analysis, we're only interested in medians and interquartile range as our measurements of central tendency and dispersion. So again, as I tell you guys always, make sure you are reading the handout or the textbook, one or the other, because there's so much information that I have on this that I really can't read all of them. So make sure you read that. So for Wednesday, we are looking to take chapter 3 exam. Your homework will close Wednesday morning at 10:30. I am still not sure if I'm going to give you the entire class period or just part of the class, because I've only made half of your exam. I'm still working on the other half. So just depending on how many questions we have in there, I will let you guys know on Wednesday if we're doing the whole class or just half the class. For it, especially because this one doesn't have any graphing, and graphing is what really takes us a really long time to do. You will probably have one box plot, right? I mean, I can't give you too many of those. So if we get time, we may actually do half a class and maybe at least start chapter 4. Okay. If you have any question, I will be on campus today till about 2 o'clock. I'll be here, I think, almost all day tomorrow. So if you have any questions, let me know. Okay. Have a great day, guys. Be careful. If you have time, stop by and make a stress ball and play some games. Come on.